Hello, my name is Kerry Howren, and I am a program manager at Materials Research and Design in suburban Philadelphia. The Navy has asked our company to develop a hypersonic aeroshell material that is capable of delaying boundary layer transition from laminar to turbulent flow. We have successfully fabricated and tested specimens which demonstrated the ability of our material to significantly absorb the applied pressure wave. These exciting results indicate that the material solution we have developed has the desired capability to delay boundary layer transition and thus provide an important enhancement to current hypersonic vehicles, specifically to enable them to fly faster and farther. What I'm asking from you as you listen to my presentation today is that you think of just one person that needs to know about this technology and how it can impact the effectiveness of mid or intermediate range boost glide hypersonic vehicles. I'm asking that you please pass this information on to that person and encourage them to reach out to me. Or if you are that person, please send me an email to set up a time where we can talk about this in more detail. Before I discuss more about the specific technology that we are developing for the Navy under the SBIR program, I'd like to take a minute to tell you a little bit about MR&D. We are a small business that has been providing research and design services to the advanced materials community for over 25 years, with a focus on high-temperature composite materials for the aerospace community. One thing that makes us unique is that approximately 60% of our engineering staff are career employees who started with MR&D right out of school and have now been there for 14 or more years. This is a testament to both the excellent working environment and the exciting variety of projects that we are exposed to. The continuity of knowledge has helped MR&D become an industry leader in composite micromechanics and simulation technologies. In addition, MR&D has extensive experience in the coordination and planning of fabrication and testing of both subscale and prototype components in relevant environments through good working relationships with a variety of material suppliers and testing houses. As a small business with a staff of highly skilled, multifaceted engineers, MR&D is uniquely positioned for lean, responsive analysis and design work to support your company and your customers' needs. Okay, so now let's talk more about what it is that the Navy is looking for. There are large uncertainties in the boundary layer transition that occurs during hypersonic flight that lead to conservative aeroshell designs that penalize flight performance. Therefore, the Navy is interested in developing aeroshell materials that are able to successfully delay boundary layer transition on hypersonic boost glide weapons by reducing the second mode instability. Second mode disturbances dominate the primary instability stage of transition in mid or intermediate range boost glide vehicles. Therefore, the expected transition targets include the Navy's Conventional Prompt Strike Program, DARPA's Tactical Boost Glide Program, and the Air Force's Advanced Rapid Response Weapon Program. In addition to attenuating instability over a relevant range of velocity and altitude, it is also important that the solution being developed has comparable mechanical properties, thermal protection capabilities, and roughness to current state-of-the-art aeroshell materials. Over the last 20 years, hypersonic boundary layer transition delay strategies involving ultrasonically absorptive materials have been investigated using theory and numerical modeling, as well as bench tests and wind tunnel tests. For the second mode instability, porous surfaces have been shown to stabilize the disturbances through ultrasonic absorption. Early work in this area used metallic surfaces with micro-drilled holes, which is clearly not a suitable solution for an aeroshell application due to the high temperatures experienced. More recent work involved carbon fiber reinforced carbon matrix composites, or carbon-carbon, which is a potential candidate aeroshell material. The critical aspects of this technology development effort are determining feasible approaches to achieving the desired surface porosity in a suitable aeroshell material and ensuring that the porosity does not compromise the mechanical and thermal performance of the aeroshell. This technology will improve the expected performance of current hypersonic boost glide vehicles under development by reducing the thermal loading associated with a delay in the boundary layer transition from laminar to turbulent flow, which will allow for either reduced insulation weight, a wider range of feasible trajectories, or potentially both. There are two critical components to the technology we are developing. The first is the methodology to achieve the desired surface porosity in the candidate aeroshell materials. MR&D has two potential solutions that are being pursued. One is a porous carbon-carbon material, and the second is an insert of a porous material into a carbon-carbon aeroshell. The second component is the development of the analytical tools capable of determining the effects of a prescribed surface porosity for a given trajectory, which will allow for the tailoring of the proposed technology to a variety of potential applications. The images here show evidence of the effectiveness of the surface porosity using a wind tunnel test model with a smooth surface on the top section highlighted in red in the top image and a porous surface on the bottom section as shown in the top right image. The images on the bottom are a resonantly enhanced shadow graph showing the boundary layer transitioning on the smooth surface while remaining perfectly laminar on the porous surface. So what have we accomplished so far under this SBIR funding? We've successfully fabricated a number of test specimens using 3 different candidate materials with a variety of porosity configurations. These specimens have been subjected to ultrasonic absorption testing, which demonstrated the ability of the candidate materials to significantly absorb the applied pressure wave over a range of pressures and frequencies of interest. While the values on the absorption coefficients have been removed from the plot on the right, it shows a qualitative comparison for 3 specimens with different porosity configurations. This shows that the configuration plotted in black performed best with the highest absorption coefficient. In addition, MR&D has also developed stability models that are able to account for surface porosity, which are being used to predict the expected reduction in growth rates compared to the baseline smooth surface model over a range of frequencies. This technology is currently at TRL 3. Proof of concept has been demonstrated both analytically and experimentally. During the remainder of the Phase 2 program, MR&D plans to perform wind tunnel testing to demonstrate the ability of this technology to delay boundary layer transition in a relevant environment and achieve TRL 6. The ultrasonically absorptive Aeroshell material being developed by MR&D will meet the needs of the Navy by successfully delaying boundary layer transition on hypersonic boost glide weapons by reducing the second mode instability. This will result in decreased operating temperatures, which will reduce the vehicle weight by allowing for a reduction in the required insulation thickness needed to maintain internal temperatures. In addition, delayed boundary layer transition results in a more controlled flight and also allows for a wider range of trajectories to be pursued. This technology will allow for mid-range boost glide hypersonic vehicles to be able to fly faster and farther. So what needs to happen to transition this technology beyond the Phase 2? The most likely way for this technology to make it onto an actual vehicle is for it to be sold to a vehicle prime or system integrator. Additional design work would be needed to tailor the porosity to the vehicle of interest, and prototype test articles would be fabricated and tested. Additional wind tunnel and arc jet tests would need to be performed to simulate representative conditions for the selected vehicle, and flight experiments may also be needed since ground tests cannot reproduce all aspects of flight. While we do have good working relationships with the hypersonic vehicle prime contractors, here is where I'm asking for you to help. If you're someone that sees a path forward for this technology, please reach out to me today. While the technology being developed here is specifically tailored to mid or intermediate range boost glide hypersonic vehicles, which means that the potential applications for near-term use are all within the DoD, there are also commercial space companies that are developing vehicles capable of hypersonic flight. As operational needs for these vehicles increase, there may be a need to develop aeroshells with the appropriate surface porosity to delay boundary layer transition, to reduce thermal loading and the associated insulation weight, and expand the performance of those vehicles. What is the business model for this technology? First, we need the hypersonic vehicle prime contractors or system integrators to transition. We are hoping that the successful wind tunnel testing, along with the analysis showing the feasibility of this technology for a generic set of hypersonic flight conditions, will entice a prime contractor to make an additional investment. That additional funding is needed to develop appropriate aeroshell designs for a specific vehicle of interest based on the design requirements and flight conditions to be provided by the prime contractor. There are several agencies that are interested in this technology, including DARPA, the Air Force, and the Navy, as this enhanced aeroshell technology applies directly to one of their vehicles. In addition, the Missile Defense Agency may also be interested in this technology for its glide phase interceptors, which are intended to counter a hypersonic weapon during its glide phase of flight. Thank you very much for taking the time to listen to this presentation and to learn a little bit about both MR&D and the technology that we are developing under this SBIR program. We are very excited about the progress we have made in developing an aeroshell material that can delay the boundary layer transition to allow for hypersonic boost glide vehicles to fly faster and farther. I hope that you heard something interesting today that raised a question or made you think of a related problem that you've encountered. If you did, I'm asking you to please send me an email or give me a call and introduce yourself or ask your question so that we can start a conversation. MR&D has a wide range of analysis and design capabilities, and I am confident that there is something we can offer to help you.